All right, everybody, so this is video 4.2, part 1, and we're starting to discuss rotational kinematics. And rotational kinematics is not that different from linear ideas. We just kind of look at things in a different way. So with linear ideas, we moved in a straight line, so translational motion is what we describe as kind of moving in a straight line. So we kind of established like location, based on like a number line. So at this point here would be like x equal to positive 3. For rotational ideas, we don't have a straight line, number line. We use in math what's called the polar coordinate system, which basically has a distance away from the origin. So that is represented by a letter r, which is usually representative of like a radius. And then the angle that point forms with the axis. So just like we did in math class, if you're going around a circle, 0 degrees would be on the positive x-axis. And as you went around, you would count kind of going around. This would be like 90 degrees, 180 degrees, 270, and 360. So going counterclockwise around the circle is going in the positive direction. If you went the opposite way, that would be like negative 90, negative 180, continuing around negative 270, and negative 360. So, so that's kind of our normal way to look at things, and you're probably more familiar with degrees than what we're going to use, which is radians. So if you remember pi radians from your algebra or trig or pre-calc class, then it talked about kind of like pi over 2 and pi and 3 pi over 2. So it's just a different way to measure. It's a different unit of measurement. There's a video that I could show you. I actually tried to show it in this video before, but had some copyright infringement ideas, so they got upset with me, so I had to replace this video. So anyway, it's just a measurement. A radian is a measurement of an angle, and it's just kind of the radius of the circle to the arc length. So that's the ratio. But I'll put a video in there if you were interested to figure out what a radian is. But the idea is that we use an angle and a distance r to locate a point in space in the rotational sense. So anyway, we are going to kind of examine the same major ideas that we did in linear kinematics. So we're going to examine displacement and velocity and acceleration and the equations that go along with them. So it's not really any different than what we did with linear. It's a really actually good review for the linear concepts. It's just now, instead of dealing with meters and meters per second and meters per second squared, we use radians and radians per second and radians per second squared. You don't have to do anything with your calculator right now. You don't have to change any modes or anything. It doesn't come up until later. So one of the first concepts we talked about in linear motion was displacement or change in position. So like we had this position, this blue dot here, where the object is at like positive 3 and it moved to negative 1. When we did displacement, it was the final minus the initial. So it was negative 1 minus a positive 3, which would be a negative 4 meters. So it moved negative 4 spaces or meters in that direction. That was the displacement. For angular displacement, we are displaced through an angle. So we're going to rotate and move through an angular space. So that's going to be delta theta. So you kind of need to know your angular position that you start with. So the initial and the final. And again, it's the same type of equation where you subtract and find the difference. Okay. We do have this concept called the right-hand rule. So the right-hand rule determines the direction of the motion, and we can use that for any vector. I'm going to talk about that in a second. But essentially, you need to use your right hand to locate the direction. So it's just a method so that you can be consistent with anyone who is in any frame of reference based on the rotation. So you'll always get the same type of answer with the same direction. Okay. So going through the right-hand rule, again, you're going to use your right hand. So these are all pictures of people's right hands. So this is your right hand. And what you have to do is you're going to curl your fingers or curl your fingers in the direction of the rotation. So if you look at this wheel, it's rotating kind of in that sense. And we'll do a demo of this in class. But the wheel is rotating in that way, and you curl your fingers, you make your fingers turn or bend in the direction of the rotation. So this person's fingers are curling the same way as the wheel is turning. And your thumb points in the direction of the vector. So the vector is actually not in a rotational direction. It's not like in clockwise or counterclockwise. It's the direction of your thumb and the way it's pointing. So this thumb is pointing in that direction or to the left. So the left would be the direction of that. This is a top here, like a spinning top, a picture of top, and the top is rotating in that way. So so we have to curl our fingers. Again, this is their right hand. You're going to curl your fingers in the direction of the spinning or the rotating body, and your thumb points in the direction. So this would be down for that. So that's kind of the idea and what you should be doing. It's going to be weird, but I'll talk about it more in class. It'll make more sense. It's not too difficult. Once you've practiced a little bit, we'll be fine. Okay. So we talked about angular displacement a little bit, or rotational displacement. So the idea here is that we can link our rotational motion or how much you rotate, so some portion of a circle you're going to rotate through, and relate that to what that is for an actual tangential or a linear kind of distance. So this isn't linear, it's a curve, but we could measure, like if we took a string and wrapped it around the circle, we could stretch it out and we could measure, okay, how far is that section of the circle that we move in meters? And that would be something known as the arc length. So again, this is going back to rotational motion, but the relationship is rotational versus linear. The relationship is this arc length S, so like the green arc that it forms, is the radius of the circle. So the radius of the circle would be from the center to the edge of the circle times the angle that it goes through. So this angle or change in times the R, so S is equal to R. If you look at the units here, R is measured in meters. Theta is radians, and radians is really a measurement of meters over meters. So meters over meters is really not just one. So it's just a placeholder. So meters for R and S is a distance, linear kind of distance, so that's in meters as well. So it works out that way. This relationship builds into other ones. So this one's talking about arc length and angular displacement and the ratio between them, which is based on the radius. The other ones that we're going to get into deal with velocities and accelerations. So it's mostly just dividing by time and getting those kind of ideas. So the next concept that we talked about in linear ideas were kind of speed and velocity ideas. And most of the time we dealt with velocity, we'll still do that. So with linear motion, or like if we had a constant velocity, we would just take the distance or the displacement and divide it by time. So velocity was displacement over time. If we were walking or moving in the x direction, it was x. If it was y, it'd be y. But this is for like an average or a constant velocity, so no acceleration here. If you wanted to do that with the circle and figure out your like instantaneous velocity, so it's going kind of that way and that way. So the direction of the velocity is changing, but this rate at which it's moving, that's sort of what we're doing. That's going to be the change in S, so like how big of arc you travel divided by how much time. So that is equivalent to the angular idea. So for angular velocity, it's the symbol omega. So omega is this cursive W kind of look. And that's like delta theta over delta t. And really the way I want you to think about this is don't treat this as a whole new section of learning physics. Like we've already studied kinematics. So we've already learned displacement and velocity and acceleration. And now it's kind of like if you were bilingual, which I'm not, you would just translate that word or that concept from whatever your native language is into your second language. So for displacement, now that's going to become delta theta. So like this is the angular version, and this is the linear or tangential version. For velocity, that would translate into omega. So, and then acceleration is going to go into alpha. So it's really just like learning a different set of symbols for the same concepts. And there are some subtle differences because it is a slightly different concept of going in a circle instead of going in a straight line. But if you treat it like this, where it's just translating it, it makes it easier for you to kind of connect those concepts together, which makes it easier to understand. So instead of like doubling your knowledge and understanding of what's going on, you're just building on what you already know, and it's a slightly different situation. So again, kind of omega is angular speed. This is the angular concept of velocity. That was the displacement was still like delta theta or delta x, and then time is still time. Time is a universal concept. It doesn't matter. We just rate that as t. So if you think about these units, omega is going to be measured in delta theta is in radians or rads, and delta t is time. So rads per second is the unit that goes along with angular speed. Again, this is like a constant one where we don't have acceleration. We'll eventually introduce acceleration. The relationship between these two concepts, so the tangential velocity or how fast you're moving in a straight line along the path, so the tangent to the circle, and the omega is r. So this is very similar to what we did with s is equal to r delta theta. Basically, all we did was divide both sides by t. And the speed divided by the time is the velocity, and then not the speed. The arc length divided by the time is the velocity along the path tangent to the circle. And then for theta, that's the angular displacement divided by the time, and that's going to get you omega. So it's really the same kind of relationship. You're just dividing by t. Introducing acceleration to you guys, that was another concept that we talked about a lot. And acceleration was just, again, how rapidly you change your velocity. So we can have accelerations with something moving in a circle. So it's going in a circle and it's getting faster or slower as it rotates. The part with acceleration is it's just, you're recognizing there are many different types. So for tangential acceleration, that's the change in velocity or the change in time. So you guys are familiar with that concept. So it's the rate at which you're traveling or changing the position divided by that time again. So it's like how quickly you're changing your time. For accelerations on this, to make it go faster or slower, you have to either push in the same direction. So if the tangential acceleration and the tangential velocity, if these two agree, that's going to go faster. If they disagreed, so if this tangential acceleration went opposite to the velocity, that would be disagreement, and I would slow down. So this would speed up, and the other one that I just drew here would slow down. So that's what it's talking about. It has to be parallel or antilateral. For the rotational ideas, it's, again, very, very similar. So our rotational direction would be going this way. So according to the right-hand rule, we'd grab the wheel with our fingers going in the rotation of the direction of this particle, so it's rotating around that path. So we would curl our fingers in that direction. Our thumb would point towards us out of the screen. So that's what this is talking about here. So again, that's omega because it's rotating that way. If we wanted it to go faster, we would have an acceleration that would agree with that. So if we had our acceleration go in the same direction, and our acceleration term is now known as alpha. So alpha is the angular acceleration. It's the rate of change of the angular speed. So this is how quickly the angular speed is changing. Again, these concepts are analogous or very, very similar. And the units make sense too. So meters per second squared was our unit for linear acceleration. For angular, it's going to be rads per second. And that's what we had before. We had meters per second. Now we have rads per second. So this is rads per second squared. And you have a direction, positive and negative, based on your right-hand rule. So those two concepts, again, if they agree, if the angular speed, omega or w, and the alpha, if they point the same direction, that speeds up. if they're going opposite ways, so if I drew in a different color here, so like if our angular speed in red, was going this way, so it's still rotating that way, but we had a alpha that went the other way, so alpha and omega are going opposite ways this time. That's disagreement, so that would be slowing down. So, so those concepts still make sense, and it's not really any different. It's the same ideas that we learned before. It's just now instead of going in a straight line, you're going in a circle. The relationship between the tangential acceleration, so that's this here, AT. So the tangential acceleration is at the tangent of the circle, so that's touching at a point. So AT is equal to R alpha. And again, we've had a similar relationship when we had S, R theta, and V, R omega. So all of these things, basically you take the radius of the circle and multiply it by the angular idea to get the linear one. So the other part that's a little bit tricky here is with accelerations in this sense, we have actually several accelerations. So we have the tangential acceleration, which is what we've been talking about here. We have the angular acceleration, which is alpha. And then we also have, because it's going in a circle, we have centripetal acceleration. So we talked about that, I think, last week. So centripetal acceleration is that acceleration directed towards the center of the circle. So if I draw this out, if we had a circle and something's rotating around that from one point to another, there is a acceleration maybe going tangentially to make it go faster. So if omega was going that way and alpha is going that way as well, it's going to speed up. The tangential acceleration is directed that way. And then there's also this radial or centripetal acceleration. So those two have to add together to get the net acceleration. So you have multiple accelerations here, and you just have to do a little bit of trig. That's all that's saying. So it's basically the Pythagorean theorem. So you have the part of the acceleration that's directed towards the center. You have the part of the acceleration that's directed along the circle, and you can turn that into a right triangle and find the net acceleration. So so that's what's going on there. All right. So so anyway. The other part of this is just kind of going back through our strategies and solving problems. So with kinematics, we drew our picture, we set up our table. Oops. We set up our table with our 5 variables, and most people by the end of kinematics were like, oh yeah, I get this. This makes sense to me. I can do these kind of problems. You need 3 out of the 5 variables. You plug in the 3 things that you know. You can solve for whatever you're looking for, and you're good to go. Those equations haven't changed. So this is one, it might have been in VF equals VI plus a t for, or delta t for the equation, but it's the same kind of concept. Those equations just are translated into the angular ideas. So for the angular ideas or the rotational ideas, delta x becomes delta theta, VI becomes omega I, or WI, VF becomes omega F, A becomes alpha, and T is still T. So it's still the same concepts. You need 3 out of the 5. So all we do is translate those equations. So if we had VF, it'd be omega F. If you like the I's instead of the O's, that's fine. So you have omega I, and then you have alpha for A, and then T. So those same equations work out to be the same concepts, and you solve them exactly the same way. You just have to be careful with your directions, just like you did with linear stuff as well. So second equation, again, you can see this. Usually we moved this over and it became like delta x. So we subtracted x minus xo, and that's just delta x, equals VOT plus 1/2 a t squared. So in this one, it'll change into the rotational version. So delta theta is equal to omega naught t plus 1/2. So these equations really don't change. It's just translating it. This is where that mindset really helps you. So instead of doubling kind of the number of equations you know for kinematics, it's the same 4 or 5 equations that we learned before. It's just now using different letters for the same thing. So it's a different language, but it still has the same meaning. Okay. All right. So let's get into a couple problems and we'll wrap up this video in the next hopefully 10 minutes. So in this situation, it says there's this ball on a string and it's rotating. It looks like in the counterclockwise direction. And counterclockwise is actually the positive direction for rotational ideas. And I don't know if I went over this, but we said 0, yeah, we did. 0, 90, 180, 270, 360. If you go around the circle that way, that's the positive direction. So as you're going around the circle in that direction, if you went the other way, those would be negative quantities. So, so positive is counterclockwise. That's a little confusing to people, but that's just the way it works. All right. So at this point, we want to know which way is this blue ball moving. That's the direction of the instantaneous velocity. So if it's going in a circle, the tangential velocity or VT is going to go tangent to the circle. So it looks something like that. So it kind of looks like mostly left and a little bit down for that one. The direction of the angular velocity, we already know that's going that way. So that's omega. So it's going counterclockwise or the positive direction. For C, it says, what is the direction of the tangential acceleration? And we're making an assumption that this thing is speeding up. So to speed up, we have to have our tangential acceleration agree and point the same way as the velocity. So if we want it to speed up, we need agreement. So it's going sort of in the same parallel direction to VT. So it's kind of leftward and a little bit slightly down. The angular acceleration, we want that to go the same way that it's rotating to make it go faster. So alpha is going to be also positive and counterclockwise. And then centripetal acceleration, that's always directed towards the center. So that green arrow is the centripetal acceleration is pointing towards the center. So that's always, always, always towards the center of the circle. And then the overall direction of the acceleration is like the net. So you need both the acceleration, so you need the centripetal and the tangential. So if you kind of put the blue and the green together, so green was AC, and blue was the tangential. So the net of that would kind of go in that direction, so down and to the left. So that's the net that I just drew in with that dotted black arrow. All right, so that's if it was speeding up. Now we're going to change it so that the particle is slowing down. So let's think about the things that were happening. So this ball on the string is still going in the same direction. So the instantaneous velocity is still the same. The angular velocity is still the same. That hasn't changed. If it's slowing down, though, we want disagreement. So if we had it disagreeing, so if I just draw another one here, because I think that's easier than trying to. So this is our circle, and the ball is like there along the string. And it's, we said the tangential velocity is still going the same way. The angular velocity is still going the same way. But this time we want the particle to slow down. So if we want it to slow down, I would have to push against it, and I'd have to have my tangential acceleration go the opposite way. So for, I think, C, it'd go kind of up and right. So it's the way I kind of drew it in that picture. For alpha, I would want alpha to go the opposite way. So it's going to go reverse to omega. So for D, omega is going to go in the negative direction or the clockwise direction. Centripetal acceleration, that's still the same. It's always towards the center. But our overall picture for part F has changed. So for part F, we have the tangential acceleration kind of going up and to the right. Our centripetal is still kind of down towards the center of the circle. And we have to get the net. So the net would be like that. So the net acceleration would go, it looks like rightward and downward. Right? So it just kind of flipped this, instead of going down and left, it was going down and right. So hopefully those concepts make sense. Now we're going to get into a problem or two. So the first problem that I want to do says, with the aid of a string, a gyroscope is accelerated from rest to 24 rads per second in 0.5 seconds. And we're going to try to figure out the angular acceleration. Angular acceleration is alpha. And then how many revolutions does it go through? So revolutions, that's going to be how many times it goes around the circle. How many times it goes around the circle, so that's going to be delta theta. So again, this is just a kinematics problem, so we're going to set up our table. Instead of having delta x, we have delta theta. Instead of having v, we have omega I, omega f. Instead of having a for acceleration, we have alpha for angular acceleration. And and then our time is still the same. So reading through this, it starts from rest, so the initial velocity is 0, the final velocity is 24 rads per second and 0.5 seconds. So everything is in the right units. You always want to work in radians with this, and then you can convert at the end like we will in part B. So we're looking for the angular acceleration. So we want the equation without theta. So without theta, it's this formula. So the velocity final equals the velocity initial plus the acceleration times the time. Again, that would be this equation if we were doing it linearly. And it's just translating it into that new language. So we're not going to worry about the linear one though. We're going to plug into this. So 24 equals 0 plus alpha times 0.5. Excuse me. So we're going to divide through by 0.5 because 0 is nothing. Divide through by 0.5. And we get alpha is equal to 48 rads per second squared. And just to show you that that's right, there we go, so 48 rads per second. So that's part A. Part B is how many revolutions. So we just got to get delta theta. We can use any equation we want for delta theta because we have 4 out of the 5 now. So the one that I like is this one. So half VI plus VF delta T, that's what it would be linear. So it's delta theta or is equal to 1/2 omega I plus omega F delta T. So you plug in delta theta is what we're looking for. 1/2 omega I starts from rest, so that's 0. The final speed that it reaches is 24 rads per second, and it's going for a half a second. So when we do that math, half of 24 is 12, half of that is 6. So it's 6 radians, and then we have to convert that into revolutions. So just to talk about radians to revolutions, the easiest way to do it is just this conversion factor. So you take 6 radians, and in one circle, if you go around a circle one time, there are 1 or 2 pi or 6.28 radians per 1 revolution. So that's just 2 pi. So if you go around the circle once, that's 2 pi. So if you divide by 6.28, that's going to get you the right answer. And you should get 0.955 revolutions. So 6 is slightly less than 6.28. So that seems to be less than 1 revolution. And that's the right answer too. Okay. So that's one type of problem. We can also have some other ones. So we'll do this other one too. So this one connects it to the linear to the angular a little bit more. So calculate the linear acceleration of a car. So we're looking for just the linear acceleration. 0.2 is the radius of the tire, and the angular acceleration is 17, so that's alpha. So to get A is equal to R times alpha, so 0.2 times 17, and when you multiply that out, you'll get 3.4. It's the acceleration for linear acceleration is meters per second squared. So that is the correct way to do that part. Then we're getting into kinematics a little bit more. If we set up our table, again, we use angular concepts, but it's still just displacement, velocities, accelerations, and times. It's just different letters for it. So it says how many revolutions, so again, we're looking for revolutions. That's delta theta. Do the tires make in 2.5 seconds if they start from rest? So rest is 0. We know the angular acceleration is 17. So we're good to go. We just have to solve for theta. We want the one without omega f. So that's this equation. So delta theta equals omega I delta t plus 1/2 alpha delta t squared. This is 0, so that goes away. So delta theta is equal to 1/2 of 17 times 2.5. And this will give us our answer in radians. And you get 53.125 radians. And then we, again, just do that conversion, get into revolutions, so divide by 6.28 rads, so the radians drop out. And when you do that, we'll get a result of something like 8.46 revolutions. So these couple questions asked you to convert a little bit more than what I probably would, but that's okay. All right, so continuing on, part C wants to know the final angular velocity, so we're looking for omega f. We know everything else, so the easiest one is probably the one that's already set up for just omega f, so it's omega f equals omega I plus alpha times delta t. So you plug in, that's 0, alpha is 17, t is 2.5. You're just multiplying 17 by 2.5. You'll get 42.5 rads per second for that one. And then the final velocity of car, velocity, not angular velocity, is v, f. So if we want v, we just do the r times the omega. So again, it's just the relationship linking the angular to the linear. So if you multiply 0.2 times our 42.5, we'll get the answer for that, and that's 8.5 meters per second is the unit on velocity. So hopefully you feel comfortable with working with these types of equations. It's really the same strategies that we use solving for linear kinematics. It's now just angular. So again, the big idea is just translate it into a different language. So you're just changing the letters slightly. So from delta x to v, I, f, a, and t to these Greek letters. So I'll stop there. Hopefully you guys are good. And next video we'll pick up with the concept of torque.